Okay, so let's go ahead and get started on temperature, temperature and rate. See if I can find my place here. Here we go. Okay, I think this is where we are. That's where your notes start, right? Okay. So we have talked about this a little bit already when we were talking about the different ways that you could speed up a chemical reaction. So remember with the Alka-Seltzer, one of the first things that was said was heat up the water and we can speed up the chemical reaction, and then the Alka-Seltzer will react faster. That is a good general rule. When you speed up, or if you want to speed up a chemical reaction, increase the temperature, okay? If you want to slow down a chemical reaction, decrease the temperature. And by the way, that's why we refrigerate our food, okay? Because the things that like to eat our food, if we can kind of slow down the chemical reactions that they are doing in order to eat the food, then we can slow down our food spoiling. So that's the main reason we do that. Light sticks, I don't know if you've ever tried this with a light stick before. I don't know why you would have, but if you put it in ice water, it's not quite as bright as it is if you put it in a hot water bath. So if you really want your light stick to glow really, really bright, then this is a good application of this concept. So, I mean, I think most of this goes without saying. It's not that bad. As temperature increases, the rate increases. That's a graph of what? What is that a graph of? Maybe it says here. I'm assuming it's probably the graph of this reaction right here, the CH3NC going to CH3CN. Wait, isn't that the same thing? Well, it's a little bit different. This is written in the way that these things actually connect to one another. Okay, so in the one on the left, the nitrogen is connected to that central carbon, and then on the one on the right, the carbon is connected to the central carbon, and the nitrogen is bonded to that. Okay, so they actually, the back half of this thing just sort of flipped. Okay, so it's really, it is a chemical reaction, but it involves just the rearrangement of one particular molecule. Okay, now if you think about our rate law, the way we typically write our rate law, rate equals K times, just an example here, concentration of A times concentration of B, and then we'll have exponents depending on what the order of the reaction is. But notice there's nothing in there for temperature, right? And there's no place in there where temperature is going to change the rate of our reaction. So the only thing that can change is our K, right? The temperature must change our rate constant, okay? So these rate constants, these Ks that we're talking about, they are only true for any given reaction at a specific temperature, okay? You change the temperature, you change the K, all right? And that's kind of across the board in this class. Temperature pretty much changes everything. I mean, we've talked about that a little bit so far. Temperature changes vapor pressure. Temperature changes this K. When we get to equilibrium, we're going to talk about how temperature will change the equilibrium constant as well. So basically, if you change the temperature, you change everything, usually, okay? So what we're changing here is the actual rate constant. That's what's going to change. So if you notice here, in this reaction, when you go up from 190 degrees Celsius to 250, you start with a rate constant of 2.52 times 10 to the negative fifth, and it ends up being 3.16 times 10 to the negative third, okay? So that greatly increases that rate constant. It goes up to the negative fifth to the negative third, okay? So the question then is, why is it that temperature increases a reaction rate so much? You guys have any ideas on why that's the case? I mean, we talked about this a little bit the other day. Why is it that temperature speeds up a reaction so much? Increasing the temperature, I should say. Okay, it's causing the molecules to move faster. Okay, and we kind of inherently know moving faster means a faster chemical reaction because we have, hopefully we have this vision in our heads of these particles colliding with one another as they react, right? So that's kind of the model that we have here, the collision model. And it basically says in order for these molecules to react, they have to collide. Okay? Kind of makes sense. They at least have to come in very close contact with one another. I'll say that for a certain student in 5th hour who is a little bit picky about the wording. There we go. Okay, so the greater number of collisions, the faster the rate, okay? And the more molecules we have present, obviously, the greater the probability of them hitting one another. That has to do with concentration, right? Okay, the more molecules we have, the faster the reaction is going to go. But then temperature can also affect it, okay? Because if you increase the temperature, now these molecules are moving faster, and if they're moving faster, they hit one another more often. And that's going to increase the rate. Okay, now, I told you we were going to talk about orientation a little bit more. We'll talk about it now. And we kind of touch on it a little bit when we talk about catalysts as well. But really, this may surprise you, but only a fraction of the time these molecules collide does the product actually form. Okay, most of the time when these things hit one another, they just kind of bounce off. And so, as you can imagine, there have to be an enormous number of collisions in order for these reactions to occur as quickly as they do. I mean, if you think about it, it just kind of staggers my imagination when I think about the fact that so a reaction like sodium azide, I think that's how you say that, NaN3, do you guys know what that's used for? Probably not. It's used in airbags, okay? And when you give it a little bit of a spark, it actually makes nitrogen gas so quickly that it actually fills up the airbag in the amount of time that you need it to before your face hits the steering wheel, okay? That's a chemical reaction that happens that fast. And if you consider the fact that most of these molecules, when they hit one another, don't actually react, they just kind of bounce off of each other, I mean, that's just incredible to think about how fast that has to happen, okay? I mean, baking soda and vinegar, you put those two things together, it instantly bubbles, okay? There's a lot of reaction taking place there, but most of those molecules, when they hit one another, they're not actually reacting, okay? So you've got to have the right orientation on these things, which means the more collisions you have, the more likely you are to have a collision that has the correct orientation, okay? And they have to hit each other with enough energy. We're going to talk about that a lot more in a minute. But here is an example of a chemical reaction. You've got chlorine plus NaCl, and that's reacting to form nitrogen monoxide and chlorine gas. Okay. Now there's two possible ways these can collide. One is helpful, one is not. And here's kind of a picture of this. Now again, you don't have color on your paper, but did you guys get a chance to write down what you need to write down there? Or was there anything to write down there? Two possible ways. Okay. So here's one possible way. The green are that represent the chlorines. Okay. Which again, on your sheet, you can't see that, but you can see it on the video. So, so if you've got the two chlorines actually colliding with one another, okay, if the molecule is oriented that way, then this collision will actually result in a chemical reaction, because then the chlorines combine, they form Cl2, and then you end up with the NO gas. Okay. If the chlorine hits the nitrogen instead, nothing happens. They just bounce off of one another, and it's just an ineffective collision. Okay. So that's kind of the idea there. Now, slightly oversimplified, okay? I mean, we live in a three-dimensional world, so obviously there are more ways these things can collide. But the idea is the chlorines need to come into contact with one another in order for this chemical reaction to occur. If they don't, if the chlorine and the nitrogen hit one another instead, then, that's not going to work. Okay? So that's kind of the idea there with the orientation thing. They have to be turned in the correct way. All right. So then we've got Arrhenius. Arrhenius, pretty smart guy. He realized that. By the way, do you guys recognize the name Arrhenius from anywhere? Talked about him a little bit this year. Arrhenius comes up usually when the names Bronsted-Lowry come up, or when the name Lewis comes up. Any bells? he came up with a definition for acids and bases that we no longer use, typically. But it was kind of the first acid-base definition that people used, and then Bronsted-Lowry came up with kind of a better one. But he did come up with that. He also did a lot of work with activation energy, okay? And he said that molecules have to possess a minimum amount of energy in order to react. Now, we have actually sort of laid the groundwork for understanding this earlier in the year when we emphasized the fact that any time that a bond breaks, that requires energy, right? Okay, anytime a bond forms, there's a release of energy. So now we're going to talk a little bit more in detail about how that works, okay? So in order to form products, you have to break bonds in the reactants. That takes some energy, okay? So these molecules have to have some energy to begin with. They have to have a certain amount of energy to overcome that barrier that needs to be overcome, because you have to be able to break those bonds in order for the reaction to occur, okay? So the activation energy here, usually it's represented by E with a subscript A. That is the minimum amount of energy that you need to start the chemical reaction, okay? So an example of this, when you turn on the Bunsen burners in the back, right, there is an activation energy required there. You have to break the bonds in the propane gas so that they can start reacting with the oxygen in the air to create that chemical reaction, okay? Now, once you get that thing started, there's more than enough energy to keep it going, right? But you have to give it a little bit of a spark to begin with. That's the activation energy. You're giving it just enough energy so that those first propane molecules, the bonds can break so that they can start reacting with the oxygen, okay? And then once you've done that, it's a self-sustaining reaction. Usually the way that activation energy is determined, this is important, okay? They will ask this sometimes on the AP exam. In fact, I think you have a question on your packet about this. That's just a multiple choice question, okay? But it's usually determined by measuring the rate of reaction at several different temperatures, okay? So, and I'll show you how that kind of works when we get to the equation in a minute for activation energy. Okay, but here's an idea. Okay, we talked about this methyl isonitrile a minute ago where the N and the C kind of switch places and become C triple bonded to N instead. Basically what has to happen here is this bond right here has to rotate. The NC bond has to rotate, okay? And so you kind of have what's called an intermediate step here. Scientists like to think about, and we're going to talk about this in the next section. It's called a reaction mechanism. And this is where some of you will really start to like this, especially those of you who have maybe more of an orientation towards geometric shapes or maybe organic chemistry, where you really like to see here's exactly how these things happen, okay? Because a mechanism basically explains, okay, here's exactly how we think the reaction is occurring step by step, okay? And so what they're giving you here is kind of a mechanism. They're saying, all right, so this NC bond right here is basically starting to rotate, okay? And so here's your intermediate step right here is the rotation, and it has to rotate just enough that that bond can break, okay? That the original carbon-nitrogen bond right here can break, okay? And then once that breaks, then you can form the new carbon-carbon bond. And now you have, you know, a different molecule. You guys remember what that's called when you have the same number of each type of atom, but they're arranged in a different way? That's an isomer, okay? So this is an isomer of that. Let's see, what else do I want to say about that? Okay, the activation energy is the energy that it takes for that twist and break to occur, okay? And then this thing, when the carbon-carbon bond forms, there's going to be some energy given off at that point, because now we've got a new bond being formed, okay? So you really have to remember what we talked about before. Breaking a bond requires energy. Forming a new bond releases energy. Okay. Here is the energy diagram for this process. Okay. So notice, here's the initial amount of energy that we're starting out with right here. Okay. And then from here to here, this is the amount of energy, this activation energy right here, That's the amount of energy it takes to twist and break that initial carbon-nitrogen bond, okay? And sometimes this intermediate right here is called the activated complex, just a fancy name for it. I don't think they typically use that terminology. I haven't seen that really on the AP exam, but that more likely you would see that referred to as an intermediate, okay? But activated complex also a way to say that. And then notice it's kind of like a roller coaster, right? We're going up, we're going up, we're going up. We have to provide energy, provide energy, provide energy, and then once enough energy has been provided, then the new carbon-carbon bond forms, and that's when all this energy gets released. Okay. So overall, what is this process? Exothermic or endothermic? Does everybody see that? Okay. The amount of energy that's being released is greater than the amount of energy you have to put into it. Okay. So that's going to be an exothermic reaction. Okay. Whoops, did we just answer the question? Oh, no, we didn't. Okay, this is a different question. So look at the previous graph to help you answer the following question. What would the delta H have to be in order for the activation energy to be the same for both the forward and reverse reaction? Well, okay, let's talk about this for a second first. We just said this is exothermic, right? So we're going to have to review a little bit here. For an exothermic reaction, delta H is what? You don't have to give me a number here, but give me a sign. Okay, it's going to be negative, right, for an exothermic reaction? Okay, now let's say that we wanted to take this reaction back in the opposite direction, okay, because you can change this back. Let's say that we wanted to go this way instead, okay? So let's think about that for a second. What would the process be then? What would the delta H be? It would be positive, right, because we're actually putting more energy into it to break that carbon. Now we're breaking the carbon-carbon bond as that twists, okay, and reforms the carbon-nitrogen bond, okay? So we have to provide more energy to this thing in order for that to happen. And then the release of energy we get is not as great as the amount of energy that we had to put in, okay? So that makes it an endothermic. So in that case, if we were going in the reverse direction, the delta H would be positive. Now what this question is asking is, what would the delta H have to be if the activation energy was the same for the forward and the reverse reaction? By the way, I guess one other question here. For which process is the activation energy higher? The forward or the reverse process? It's the reverse, right? Okay. The activation energy, if we're going this direction, if we're going from right to left, the activation energy is all the way down here, right? Okay, so it's a bigger activation energy. If we wanted the activation energy to be the same for both processes, our graph would actually need to look something like this. Okay, you see how they're both at exactly the same level, right? Because then activation energy is the same whether we're going forward or whether we're going backwards, okay? So what would the delta H be for this kind of process? Delta H is 0. Does that make sense? Okay, in order for that to occur, in order for the activation energy to be the same in the forward and reverse direction, then our delta H would have to be 0. Okay? I've seen that question asked a couple of times on AP exams too. It's kind of an interesting question. So, okay. Change in energy for the reaction is the difference in energy between, yeah, we already talked about that. The activation energy is the difference in energy between the reactants and the transition state, the intermediate or the activated complex, whatever you call it. Okay. The rate of the reaction depends on that activation energy. Okay. The higher the activation energy, the slower the reaction occurs. Does that make sense? Because the higher the activation energy, the more energy those reactants need in order to actually do anything. Okay? So if you increase that activation energy, just think back to the collision model, right? These things are hitting each other with certain amounts of energy. If it's a high activation energy, you're going to have a lot more of those particles hitting one another and just bouncing off because they don't have enough energy to actually react. which is going to greatly slow down your chemical reaction. Okay. Now, what's something you could do to help you overcome that large activation energy barrier? Heat it up. Speed up the molecules, give them enough energy that when they hit each other, they can actually react. Okay? All right. And then we talked about this just a second ago. If the forward reaction is exothermic, then the reverse is endothermic. Okay? And then the exception to that is the one we talked about where the delta H is 0, so the forward and reverse are going to be the same. How does a methyl isonitrile molecule gain enough energy to overcome the activation energy barrier? Well, I guess we sort of just talked about this too. Okay. Now, there actually is an equation that you can use for this that shows the fraction of molecules that have enough energy to actually react. You guys already have this written on your paper, this bottom part, right? The R? Okay, because that's kind of up against the words down here. So this is kind of an interesting equation. I'm pretty sure this is not on your equation sheet. I think you only have 3 kinetics equations, and I'm pretty sure this isn't one of them. I've never seen them ask you to calculate the fraction of molecules that have enough activation energy to react, but it's just kind of an interesting equation because you can see at any given time, depending on your temperature and depending on your activation energy, what fraction of the molecules would be able to react at that point. Okay. And obviously, the higher the temperature, the higher fraction of molecules you're going to have that are able to react. Do you guys have this graph? Okay. The reason I didn't put that on there is because I don't know that it's that useful. But just notice this is your activation energy line right here. Okay. Any molecules that are past that line, to the right of that line, are going to have enough energy to react. Okay. So notice at the lower temperature, obviously you have less of those that can react. Then at the higher temperature, you have more of those that can react. That's all that's showing. Okay. Now Arrhenius discovered that most reaction rate data obeyed his equation. Well, he came up with an equation that correctly described most reaction rate data. Okay. And so here's his equation. Now this one, does it even have your equation sheet out? I should have mine out. Here, hang on. I'll open mine real quick. Did you guys have stuff to write down on that page, other than the equation? You did? Okay, sorry. Give me just 1 second here and I'll figure this out. I just want to see exactly what you're looking at here equation-wise. Okay, here we go. Alright, yeah, so literally the only 3 equations that you have for kinetics are these, whoops, are these 3 right here. Okay, and this one right here, that's actually a rearrangement of the Arrhenius equation. Okay, so you do sort of have it, you just have it in graphical form, which is actually a little more useful. So I'll show you what that looks like in a second here. And again, I think probably you're going to have that equation sheet when one of these questions comes up, because they'll typically ask these questions on the free response section. Okay. So K is the rate constant, which we're familiar with K. A is what's called a frequency factor, okay? And that's going to be different for every reaction, okay? And it's the measure the probability of a favorable collision. So that has to do with, you know, how big is the molecule? How many different ways are there that this thing could collide with something else? So it really takes that orientation factor into account, okay? And then EA is the activation energy, which we've already talked about. R is just the gas constant, and T is temperature. Okay, so there's your equation. The one that you're typically going to be solving for in this type of equation is the activation energy. Okay, So let me show you. Well, okay, let's talk about this question first. So we've got this series of reactions, and here's their energy profiles or their energy diagrams. Assuming that all three of these have nearly the same frequency factor, in other words, their geometry is not that different from one another, so the probability of them colliding in a favorable way is about the same. Which one of these reactions is going to be the slowest? Okay, and why number 2? Okay, now remember we said that the activation energy directly affects the rate, right? The more energy you have to overcome before the reaction can occur, the slower the reaction is. So this is going to be, we're going from slowest to fastest. Okay, so this is number 1, because that has the highest activation energy. Okay, now I have to make these things confusing. What is it saying? Yeah. Okay, alright, so there's a lot of different arrows here, but ultimately what this 20 kilojoules per mole is showing, it's showing from here to here, okay? Which, that's from the start of your reaction to the highest part of the activation energy barrier, okay? So, because that's 20, that one's going to happen a little bit slower, and then the one with the least activation energy out of all three of these is going to be the first one over here, okay? So that's going to be the fastest of the 3 reactions. Does that make sense? Alright, so we can actually rearrange the Arrhenius equation, and this is where you'd use the calculus to do the rearranging, but you end up with the natural log of k is equal to negative EA over RT plus the natural log of A. Now again, the reason it's useful to rewrite the equation that way is because now it looks like y equals, well, it doesn't exactly look like, yeah, let's see, how's it written on your equation sheet? Because they have it, I'm pretty sure they have it written in just the right way, so it looks like, yeah, see how they have it written, they rearranged it so that they separated the 1 over t, because that's typically how you'd graph it. So y equals mx plus b, okay? So if you graph the natural log of k versus 1 over the temperature, then your slope is going to be the activation energy, the opposite of the activation energy over r, and r is just a constant, okay? And then you get the natural log of a as your y-intercept, okay? So that's useful because you can actually graphically determine the activation energy of a reaction, okay? And that's why I said earlier that a lot of times the activation energy is determined by just measuring the rate of the reaction at a bunch of different temperatures, okay? Or actually measuring the rate constant at a bunch of different temperatures. You guys are actually going to do this on your lab that you do next week, okay? At the very end of this, you will measure the rate constant for the reaction at several different temperatures. Then you get to graph it, and then you get to use this equation to figure out what the activation energy of the reaction actually is, okay? Okay, so when you do this graph, natural log of k versus 1 over t, then it's usually going to look something like this, okay? And again, we're graphing the inverse of the temperature, so this graph is going to go down. If we don't have a lot of data, then another way that you can do this is you can actually figure out an equation just knowing 2 sets of data, okay? Now, did I leave you a big space to write all this down? Okay, it's already written for you. Okay, the reason for that is I don't really care that much that you understand this derivation. It's not... Anytime I've seen this on an AP exam, they've given you the data, they've given you the graph even. So all you have to do is use the slope of the graph to figure out your activation energy, okay? But if you were in a situation where you only had a couple data points, this is an equation you could use to figure out the activation energy. You know, it would be a little more approximate this way. It wouldn't be quite as exact, but you could use this equation, okay? Not too worried about that because it's not on your equation sheet for the AP exam, so they're just not going to ask you that question, okay? Alright, so we got a sample problem here. The following table shows the rate constants for the rearrangement of methyl isonitrile at various temperatures. From these data, calculate the activation energy for the reaction. And then we want to know what's the value of the rate constant at 430.0 K. Alright. So we've got 4 data points here, okay? And we've got our K. What will we need to do in order to figure this out? They're asking us for the E subscript A, the activation energy. I think maybe you know, you're just afraid to say it because it's going to be incredibly time consuming. What do we need to do here? Nobody knows? Well, okay, you can look at the equation sheet. That will be helpful. But we've got a bunch of different data points here, right? Okay. On your equation sheet, let's look back at that again and see what we have here. Let me erase this. Oh, come on. So you can see a little bit more clearly. Well, it looks to me like we might need to graph this thing. Okay? Yeah, and that's what everyone was afraid to say. So we would need to graph this. Now, we may not, just for the sake of time, because I feel bad about how long these videos have been taking, we may not go all the way through this process, but we can at least start it and talk about how we would graph it. So we've got the natural log of K equals the negative EA over R times 1 over T plus the natural log of A, all right? So what 2 things would we really need to know in order to graph this thing? Okay. Right, we need to figure out our Y here, natural log of K, and we need to figure out our X, right? And then once we have our set of X and Y points, then we can just graph this thing. And once we graph it, we can use that graph to find the slope of our equation, okay? So we would come back over here, and what we would want to do first off is find the inverse of all these temperatures, okay? And so take 1 over 189.7, and you get 0.0053. I know it's not nearly the right sig figs. Now let's do this right. I hate doing things right. That's a good idea. 5.271. There we go. Times 10 to the negative 3. And then 198.9. The inverse of that is 5.028 times 10 to the negative 3rd. The inverse of this is 4.342 times 10 to the negative 3rd. And the inverse of the last one here is 3.981 times 10 to the negative 3rd. Okay? So now we found our points for our x-axis, okay? And then we need to take the natural log of k in order to figure out our y-axis. So you just take the natural log of all these numbers over here. I'm getting negative 10.6 for that one. Negative 9.85 for that one. That's an 8. Negative 7.37 for that one. And negative 5.76 for that one. Okay? So now we've got our x values. and we've got our y values. And once you graph that thing, you should have some sort of graph that looks similar to the one on the... Well, here, let me go back here for a second. I'll show you. Should look similar to this. Actually, I think this is the graph for that. Is it? The y numbers look right. Do the x numbers look right? It doesn't quite look right for the x. Okay, so I don't think that is a graph of that, but it would look similar to this in the sense that it's a straight line sloping downward graph, okay? Then what you'd have to do, pick a couple points on that line, which they've already, sort of demonstrated. Here, let's pick this one, and let's pick this one, okay? Then you've got 2 x points, 2 y points, and you can use rise over run, your y2 minus y1 over x2 minus x1 to find your slope, okay? Now, once you find the slope, that is not your answer, okay? The slope is equal to the negative of the activation energy over r, okay? So once you find the slope, then you plug it into this equation, okay? We know r is 8.314. And then you can solve for your activation energy, okay? Does that make sense? Just because I told you that a couple of slides ago. Where is it? Is it? Okay, yeah, just trust me on that, yeah. And actually that R is listed on your equation sheet, so you don't have to memorize that number. Because again, any activation energy question like this that I've ever seen, it's on the free response section, okay? Alright, so that's that. Once you find the activation energy, then it's asking you what's the value of the rate constant at 430K. Well, once we know the activation energy, let's go back here. Okay, you know what? They didn't tell us the A, did they? Okay. So because they didn't tell us the A, then what we'd have to do is still use this equation for that second part, okay? But now that we know the activation energy, let's see, how would we figure that out? So you're giving us the temperature. Oh, okay, that's just that's just a matter of they're giving us a temperature, and based on the graph we just made, we need to figure out what our x point is, right? They're giving us this, I'm sorry, our y point, because they're giving us the x, right? They're giving us the temperature, so then we take the inverse of that. That would give us our x point. Then you just look on your line and see where that hits the y-axis, okay? And then, that's the natural log of the k, so then you should be able to use that to figure out the k. Does that make sense? Again, I'm trying not to actually go through the whole thing and solve this kind of a monster problem, but okay, so that's the general idea there. Alright, so next time we'll talk about reaction mechanisms, and hopefully that made sense, a little bit more sense than the last video that we did, and we'll see you guys in class.